Hello dear students, welcome to the video lecture series made under Professional Learning Community of Walchand Institute of Technology, Solapur. Myself, Sanjivkumar Siddul, working as an assistant professor in physics under Department of Humanities and Sciences of Walchand Institute of Technology, Solapur. In this lecture, we are going to study the topic Introduction to Nanoscience. These are the learning outcomes of this video lecture. By the end of this session, students will be able to get acquainted with the terms nano, nanomaterial and nanotechnology. Student will be able to understand the distinguished properties of nanomaterials and factors affecting the properties. These are the contents of this video lecture. Introduction. The 20th century observed an outstanding progress in technology. The very first reason behind it is the reduction in sizes of electronic circuit elements and devices. This came due to the development of currently known nanotechnology. The underlying development approach behind this is known as top-down approach. In this approach, one starts with large-scale object or pattern and progressively go on reducing its dimensions. This process is similar to sculpting a statue from a big rock. But nature adopts exactly opposite approach, that is bottom-up approach. For example, atoms combine to form molecules. Molecules fuse to form heavy molecules like enzymes, amino acids, etc. Then they fuse to form organelles and hence cells. Cells come together to form tissues and then organs, organ systems and organisms. Noticing this in 1959, a renowned physicist, Richard Feynman, presented a visionary lecture in American Physical Society entitled "There is Plenty of Room at the Bottom," wherein he said, "The principle of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom." Feynman's this discussion was the starting point of the nanotechnology. Nanoscale. The word nano is derived from a Greek word nanos or Latin word nanus, meaning dwarf or extremely small. In measurements, nano is a billionth, that is 10 raised to minus ninth part of a unit. A nanometer hence is the 1 billionth of a meter, that is 1 nanometer is 10 raised to minus 9 meter, to say 10 raised to minus 3 micrometer or 10 angstrom unit. For comparison, consider the sizes of few known objects. The size of a typical watermelon is nearly 10 raised to minus 1 meter, that is 1 decimeter or 10 centimeter, while the size of a penny is 10 raised to minus 2 meter, that is 1 centimeter. A full stop given on a paper by a pen has a typically size of 10 raised to minus 3 meter, which is to say 1 millimeter, and the thickness of hairs measure in 10 raised to minus 4 meter, that is to say 100 micrometer. A red blood cell measures has typical size of 10 raised to minus 5 meter, precisely to say 5 micrometer, whereas the size of viruses measures in 10 raised to minus 6 meter, that is to say in few micrometers. The size of atoms, bond lengths and smaller molecules are nearly or less than 10 raised to minus 10 meter, that is of the order of few angstrom unit. For example, A benzene molecule measures around 0.5 nanometer, that is 5 angstrom unit in diameter, while a water molecule measures around zero point 0.1 nanometer, that is to say 1 angstrom unit in length. Nanomaterials are having dimensions in nanometers, that is 10 to minus 9 meter. For example, a gold nanoparticle has an average size of 10 nanometer, wherein carbon nanotubes are around 5 nanometer in thickness. Thus, nanomaterials could be defined as those materials which have structured components with size less than 100 nanometer at least in one dimensions. Nanoscience can be defined as the study of phenomenon and manipulation of materials at atomic, molecular, macromolecular scales where properties differ significantly from those at the larger scale. And nanotechnology can be defined as design, characterization, production, and application of structures, devices, and systems by controlling their shape and size at the nanometer scale. The materials at nanoscale have very distinguished electrical, chemical, mechanical, and optical properties compared with the bulk sizes of their own. Nanomaterials may have lower melting point and phase transition temperatures. Usually, the crystal structure of nanomaterials remains the same as that of their corresponding bulk structure, but the lattice constants are lowered. In general, the reactivity of all nanomaterials is high compared to that of their corresponding bulk materials. This is due to their higher surface area to volume ratio. The mechanical strength of nanomaterials is higher than their corresponding bulk form. This enhancement is due to reduced defects. For example, a nanocrystalline nickel is as strong as a hardened steel. Optical properties of nanomaterials are significantly different from their corresponding bulk materials. The color of nanoparticles may change with their cluster sizes. For example, nanoscale gold particles can be orange, purple, red, or greenish depending on the size of the clusters. Generally, the electrical conductivity of any material decreases with the size, but electrical conductivity of nanomaterials can be enhanced significantly by better ordering in them. It is seen that the net magnetic moment increases as the cluster size decreases. Thus, nanoclusters are more magnetic than their corresponding bulk material. That is, they start exhibiting ferromagnetic behavior. Self-purification is the intrinsic property of nanostructures or nanomaterials. The properties of nanomaterials are very much different from those at the larger scale. This is due to following three main reasons. The first important factor is increase in surface area to volume ratio. Nanomaterials have relatively larger surface area to volume ratio than the corresponding macro bodies. This can be understood by following example. Consider a material in bulk form in the form of a cube of side length 1 centimeter, that is to say 10 to minus 2 meter. Therefore, the area of the material in this bulk form will be 6a square, that is to say 6 into 10 to minus 4 square meter. And the volume of the material will be given by V equal to a cube, which turns out to be 10 to minus 6 cubic meter. Therefore, the surface area to volume ratio will be A divided by capital V, that is 6 into 10 raised to minus 4 divided by 10 raised to minus 6, which is to say 6 into 10 raised to 2 per meter. Now let us consider the same material in small cluster form. If one such cluster is in cubic size of length say 1 millimeter, that is 10 raised to minus 3 meter, then the surface area of this small cluster will be 6a square, that is to say 6 into 10 raised to minus 6 square meter, and the volume of this smaller cluster will be V equal to A cube, which turns out to be 10 raised to minus 9 cubic meter. Thus, the surface area to volume ratio for this small cluster will be 6 into 10 raised to minus 6 divided by 10 raised to minus 9, which turns out to be 6 into 10 raised to 3 per meter. This clearly shows that the volume to surface area of material increases significantly as the dimensions of the material reduces. As the growth and catalytic chemical reactions occur at the surface, nanomaterials will be much more reactive compared with their macro bodies. This also affects the mechanical strength and electrical properties of the materials. The second factor affecting the properties of nanomaterials is dominance of quantum effect. At nanoscale, quantum effects begin to dominate. This is because of the fact that in bulk material, the number of electronic energy levels is so large and the spacing between these energy levels reduces to such a small value that they form an energy continuum, and electrons in a band are not confined to one particular energy level. Whereas in nanocrystals, there are discrete energy levels and the electrons in the nanocrystals are confined to particular energy levels. Due to this discretization of energy values of the electrons, quantum effect will begin to dominate. This dominance of quantum effect will give rise to drastic change in optical, electrical and magnetic behavior of the materials. The third factor which affects the properties of the nanomaterials is their critical length. If the size of the nanomaterials is reduced smaller than the critical length, the nanomaterials exhibit significantly different properties compared with their corresponding bulk materials. This is mainly due to change in the value of mean free path, which is the average distance traveled by an electron between two successive collisions with the vibrating atoms. These are the references used for this video lecture. Thank you.